Now, in this example, we have a gun with a spring-loaded gun, which is held vertically, and the original length of the spring is up to here, and then by some device we push the spring in up to this position, and then it's locked over here. Then we put a ball in here, or the bullet, and then the trigger is pulled and the spring pushes the ball up, reaches here, and the ball will keep going out and reaches a certain height, some maximum height, after which it falls down. The initial position of the spring, or equilibrium position, is y equal to 0, which is the point B. Let's write it a little bigger. The spring is squeezed to the point A, that's A, and after pulling the trigger it goes to the point C, and this is point D. Now we can frame this question in different ways. So in the book the question is, what is the spring constant? So let's assume that we know spring constant, we'll find the maximum height. In the book this height is given, spring constant is to be found. So you can look at that example for a separate second example. So we'll say that this is y equal to 0. So we are given y, well, at B is 0. We are given the value of ya, let's say it's 10 or 12 centimeters. So that will be negative 10 centimeters, because y equal to 0 starts from here. And then we are given the spring constant, and we are given the mass of the ball. And the question is, what is YC, or how high does it go? And let's assume that friction in the barrel is 0. There's no friction in the barrel. We could add it later if desired. So now we'll write the equation, the delta K plus delta U, and let's say that we have two kinds of potential energies, one due to the position and the other due to the spring. We have both here, equals the external work, which is 0, minus the friction, which we consider to be 0. So both of these are 0. Now the delta K would be the K final, which is C, that's our final position, minus K at A, which is our initial position, starting from here, because we pull the trigger here, then it shoots up, plus the UG at C minus UG at A, that will be the potential energy difference between these two, and then the U spring at, well, the spring is not going to go all the way up to here, so the spring is going to stop at here. So that's U spring B minus U spring at A equals 0. And now we can say Kc. So at the highest point, the velocity is going to be 0. So this is going to be 0. And at the initial point, the velocity was 0. That's 0. So both of these are 0. So that simplifies a little bit. And then the gravitational potential energy will be the mass of the ball, G, and YC, and this would be mgya. And ya would be negative, so they will actually add up, because you need the total distance. C minus ya should actually be the distance from here up to here. So it's going to be this distance plus this distance. So that's this term, plus the spring at B is going to be 0, or you can write it as half K, and the X position at B is going to be 0, half k of the spring, and that's going to be this distance from here to here. That's how much the spring is compressed. So that's going to, let's write it than x. That's going to be x squared, where x is going to be y final minus y initial, b. So it's just ya negative, but when you square it, it doesn't matter. So this goes away. Plus, with the minus sign, spring constant, and it's going to be ya squared. And so we're looking for yc. So we know the mass, the g, the ya, which is minus 10 centimeters, whatever. It converts to meters. And the spring constant is also known. Ya is known. So we can solve this equation to get the maximum height. Consider the case where friction is not zero. In that case, we will have the same equation, mg yc minus ya minus half k ya square, but now instead of being 0, it's going to be equal to this fd, which is now not 0. So if we know the force of friction, this is not going to be a mu n case because there's no normal force. So we'll have, if we know the value of friction, and the d is going to be, or the distance is going to be from here, from A to D. That's the length inside the barrel in which the ball will experience friction. So it's going to be yd minus ya, and an absolute. So if we solve this, we can get the value of yc. Now, the next example, we consider a horizontal surface with a weight sitting here, a pulley here, there's a string going over the pulley, and we have a bigger mass here. Well, it doesn't have to be bigger. That's m1, that's m2, and there's a force pulling it backwards, and there is friction backwards, but this mass is going down, even though there's a force here, but this is large enough that it's going down, and this is moving to the right. So the question is, what is the speed of m2 or m1? Both will have the same speed after m2 falls by some distance, d meters. So that's the initial position, and it will go down to some final position, and this distance is d. So the bottom goes from here to here, that's the distance d, and this will also move forward by the same distance d. So now let's write the equation. We want to find the velocity at this point. So that's the final condition, that's the initial condition. So we have the vi initial. Things that need to be given to us are m1, m2, the coefficient of kinetic friction, the value of the force pulling it, the angle theta, m1, m2, and v initial. That's we should know. Now with this information, we start right. We can solve this by equations of motion also, Newton's methods. We can also solve it by here, by the energy method, delta K, delta U. There's no spring here, so it's only UG. There is external work, this one, and there is friction. Now the delta K, we have two masses, so there will be two kinetic energies. So we should rewrite this as delta K1, delta K2, and then there are two masses, so there will be 2 delta UG1 and delta UG2. There's only one external force, so there's only one external work, and well, one friction, because there's no friction over here. Only friction is here. If there were friction here, we would add that friction over here. Now the delta K1 is going to be half mv1 final square minus half m1 v1 initial square. Okay, so that's the increase in kinetic energy of number 1, plus half m2 v2 final square minus half m2 v2 initial square, so that's the increase in kinetic energy of number 2, plus ug1. So the change in internal potential energy of number 1 would be m1g y1 final minus y1 initial, and they are the same because it's moving horizontally. If this were not horizontal, then we would have something here. And then we come to the delta UG2, so it goes from here to here. It's going to be M2G Y2 final minus M2G Y2 initial. Okay, I wrote this like that, but it's the same thing. The work external is this way, and the work is going to be the x component times the distance, f cos theta times the distance d would be the same as the distance d that it goes this way. Now, this work is going to be negative because the force is pulling to the left, that's Fx, but the displacement is to the right. So there will be a negative work, and the friction will also be negative. So let's just write Fd. But we need to get F, and we see that this is M1, we have a normal force, we have an F which will give us an Fy and an Fx, and we have an M1G, and we have a tension pulling to the right. So sum of forces in the y direction would be the normal plus Fy minus Mg equals 0, and therefore normal force is Mg minus Fy, and therefore the friction is mu times N, and this is Mg minus F sine theta. So plug that in here to get here, N, and then the friction, and plug that here. Now let's see, in this equation we are given the initial velocity. So this is, well, that's for number 1, and number 2 would have the same speed. Okay, here these are not the velocities because we are squaring them, so these are the same. V final would also be the same, and that's what we're looking for. So let's simplify that. So we can combine these two together and say half m1 plus m2 v final square. Okay, these two would be just the same, so it's v final, and half m1 and 2, we take that. Then we can have minus half m1 plus m2 v initial square, so that's adding these two together, that goes, plus m2g, and it's the distance d, 2 final minus 2 initial, so that's going to be d with a negative, so we can change that to a minus d. 2 final minus initial will be negative d, that's this term, and then we have equals minus f d cos theta and minus fd, where the friction is given by here. Now, based on what we were given as the initial conditions, we know the masses, we know the initial velocity, we know all of this, we know these, and we know all of these, and therefore the only unknown is v, which we can solve and find. Now, if there were no friction, well, we just remove that term. Now, as a last example, let's consider an object that's sliding down and then goes along the floor and it stops over here. And it starts from a zero velocity, it accelerates, and then this is smooth turf, and then it goes along the floor and stops here. The friction coefficient here is mu k1 and here it's mu k2, so the friction could be different or it could be the same. And we are given the theta, we're given the mass of this object, we're given the length of this part of the sloping length, and we don't know the distance along which it's going to stop, but we do know the length here. So this is our y-axis, this is y initial, and this is y final, which is equal to 0. And now we write, the question is, how far does it stop? What is d? So if it starts from an initial velocity, slides down here, it gains some speed, then goes horizontally, and will stop that at some point. Let's call this point A, this point we call B, and this point we call C. Now, let's write the delta K plus delta U, and there's only the G. No external work, but there is friction. So if we solve this between A and C all along, we could solve it between A and B, use the friction for this part, get the velocity here, and then use that as the initial condition and solve between B and C and find the distance d. But we can also solve it by assuming just going straight from A to C. So between A to C. So the delta K, the initial speed is 0 and the final speed is 0. So this delta K is going to be 0. The delta UG is going to be mg y final minus y initial. So just this height. So this is the driving force. This loss of potential energy causes the whole thing to move. Now there's two frictions, so we need to get this part and this part. So it's going to be F1L, that's in this part, and F2D, that's the friction in this part. Now F1 is going to be mu times N, and in this case the normal is going to be mu mg cos theta. So we know all of that, we can plug that and get here, and we know that. And F2 is going to be mu N, let's call this N1 and N2, that's simply mu mg because it's a horizontal surface. So we know all that, and everything is known except d. So we can use this to get the distance along here. Now if you wanted to solve it between A and B first, and then between B and C, so if you go from A to B, we would just rewrite that equation as half mv at B square minus half mv at A square plus mg, and that's going to be y final minus y initial, only the F1L, only this friction. And we can use this to get, well, this is 0, we can use it to get VB. And then we go from B to C and write the same equation again. So it becomes half mvc square minus half mvb square plus mg, and now there's no change in the elevation, so that's 0, equals minus F2d. And since we already have VC, we can plug that in here, BB, plug it in here, VC is 0, and we can get the value of d. So you can break it up into two parts, or you can solve it in one part.